Okay. Good afternoon, everyone. Am I audible?
Yeah, good afternoon.
Good afternoon. So today we are at week 12, right?
Yes.
So we have already completed the course. So what today we will do first, go through that week 12, some topics of the week 12, uh, like fourth moment based approach and series and parallel system for the failure modes. To solve that week 12 assignments, and then we will focus on weekly assignments to figure out which kind of questions actually may come uh, for the final examination. So basically we will discuss on that all the assignments, and particularly we will figure it out which kind of questions we will be focusing for this mm, uh, you know uh, final examination. So my name is Devasis Panda. I am a Prime Minister Research Fellow and Research Scholar at IIT Guwahati. So let's quickly start today's session, right? So first, like fourth moment based approach form. So basically, what we have learned in form. You have already gone through the lectures of this week 12, so you will find out that the course instructor has, you know, uh, described that 40 years of development of the form, but we will not go into that. We have already gone through that Hessofer-Lane reliability index and how to solve the first order reliability problem using the Rackowitz or Rackowitz-Fissler algorithm. We are now habituated with that, and we are very familiar with that actually. So we will not spend more time on that. So basically what actually that fourth moment based approach, like here that 40 years developments uh, that actually covered by this course, like first that Cornell definition of Cornell reliability index we have seen, then the limitations of this reliability index also we have seen, that if we have changed the format of the limit state function, then the final estimate of beta may change. Then the Hasper-Lin reliability index came, and this lack of invariance problem has addressed. And now we will not go into deep into that. Okay, that thing you can go if needed, but the form and the simulation based techniques is enough for the reliability and to find out the probability of failure and reliability index. So this fourth moment based approach actually one of these developments which have been done in the past years. Like 2007 they came up with this fourth moment based approach where they suggest some approximation to the limit state function. So we will not go into it like directly, we will go to the algorithm, and what I said, today we will focus on the question, solving the questions, and figure out which kind of questions we will be more focusing on. Like these kind of questions will not come to your final examination. What is the Fisher Cornish and Cornish expression for this reliability index? And quite frankly, this kind of approximation will work for this particular problems. You will uh, try to solve different kind of problems with this kind of approximation, you will not find the convergence. So like if someone is interested to find out this kind of reliability process, or find out how we can work out this kind of reliability, so they can go through this paper here, this thing, like how they solved it, and they also add some example to this paper, how they have solved this beta and all these things. So we are not interested to go there. So just to show you why I am add these slides, just because of some questions in week 12 that is associated with this fourth moment based approach. So here basically what they have done, they actually suggest some limit state function using fourth moment based approach, and like this is familiar with your response surface method, the polynomial based approach, and they have solved these unknowns with respect to the moments. Like we have four central moments: mean, variance, skewness, and kurtosis for normal distribution, and based on this they have figured it out how we can closely approximate the limit state function using this kind of moments to get the closest form of the reliability to Hasofer late reliability index. So the, if we look into the algorithm of this expression, like here you can see, first, similar to that response surface method, but here the approximation is different. Like here start with that limit state function, and then they have evaluated that L1, L2, K1, K2. These values, how to evaluate these values, they have actually given in this paper. Then evaluate that third and fourth moment. These expressions also given in their paper, and the some limitations like uh, which domain or which range it will act. Like here for the fourth moment, they have suggested that this condition if satisfied, then the reliability estimation will closely match to the first order reliability estimation using Hasofer lean reliability index. Like mostly the records or records Fischler algorithm, actually we have uh, that convergence, like guaranteed convergence in record Fischler algorithm. Then find out that PQRZ, this kind of expression also given in there, and reliability analysis. So we will not go into that. Like if we need to solve them during the assignments, then we will go back and come back here and we will see. So main thing, we will first see like failure modes. We will spend some times on the failure modes, like one or two questions may come from this failure modes. Short type of questions like rapid fire type of questions may come from the failure modes. Now why these failure modes are important? We like in gradient based form, or like uh, using the Hasofer reliability index, what we have done, we have solved the reliability in the element level. Now, for the element level, we know what should be the reliability. Like we have solved the beam problem, like what should be the reliability index and probability of failure for the beam problem. But now the thing is, if we have the whole structure, how we can proceed? Like if we know the element level reliability index or probability of failure, how we can incorporate this information to get the overall or global level reliability or probability of failures. That is the main concept of failure modes. Like in general, we have different kind of systems like series system, parallel system, or mixed system, or quite frankly we have like mixed system. Like here for this building, if we see, like in element level, we look into the element level. Like for this beam or for this column, we want to solve the reliability. We can first develop that GX with respect to failure, like which kind of failure we are looking at. With respect to that, we need to find out the capacity and demand, and based on that, like we form our limited function GX, G of X, and that is nothing but our capacity minus demand. And capacity and demand, like if we want to look into the plastic failure, or for a beam, if we want to analyze with respect to the flexural strength. So different kind of limit state may form as per our requirement, and different kind of random variable may there. So we can work out this local level or element level probability. Now if we have the whole system, or if we want to have some understanding about how this local or element level reliability index, or using this information of the element level reliabilities, how we can work out for the whole system. So we need to identify which kind of system we are talking about for global. So we can have the system like series system, we can have parallel system, or we can have mixed system. That means mixed of series and parallel systems. Okay, so like here for the series system, series, what do you know? Like we all have seen like series and parallel system, where like that resistance and all these things we have already learned which kind of systems we call the series and parallel system. So series system, what do you know about the series system? Like just tell me, like if we have any kind of failure in this system, that govern the total failure of the system, right? So here the schematic diagram of the series system, we can see that here the n number of elements are connected to this series. Now one of these element, if one of these element will fail, then the whole system will fail. So how we can work out this kind of problems, or how we can find out the probability of failure, or that reliability. Here we define that as the probability of survival of the system. So how we can proceed with these things, that we will see for 10 to 15 minutes, then we will go to our main thing, like we will solve this question. So first, like here we have, if we have like n elements, and if we uh, categorize this element ai like one of these events associated with some elements, and probability of survival of the system pss, and probability of failure of the system, like probability of survival of the system is nothing but the reliability. Okay, now see this expression, what is that? Probability of survival of system is nothing but 1 minus probability of failure of the system. That means the reliability of the whole system is nothing but 1 minus probability of failure. Now here this system is connected to the series, like one of the element, if one of the element will fail, then the whole system, we will consider that whole system will fail. That means the probability of survival of the system, we can define it like that. Okay, probability of these events like ai are nothing but the events that associated with ith element. So probability of that total system or that series system, that means the survival, we can we can define it like that, that probability of a1 intersection a2 intersection a3. Now once we can find out the expression of this, and if we know that all the events are independent, now independent event, we can multiply the probability. So probability of this probability of survival of this total system in series, we can write it down like that, like probability of a1, probability of a2, probability of a3 up to an. And like we can multiply all these probabilities, and in other word, like we can replace this like that, that it's multiply all these probabilities associated with this thing, or we can directly replace like probability of failure of each component. Like probability of failure of each component, we can easily find it out. Like in component level, we have already worked out how we can find out the probability of failure. Like for the beam problem, we can easily find out if we know the limit state, or if we know the failure criteria, or if we know that particularly which kind of failure we are looking at, we can easily work out with this problem. And this thing like 1 minus probability of failure of all the individual component, we can uh, multiply, and we can get the overall probability of survival of the system. The probability of survival of the system in a word, like 1 minus that probability of failure of the individual system. Here we can see that like probability of failure for the series system, here 1, 2, 3 and 4 components are on this system. Now how we can find out the probability of survival of the system? It's nothing but 1 minus probability of first element multiplied by 1 minus probability of second element multiplied by 1 minus probability of third element and 1 minus probability of fourth element. That means that probability of survival of the system, we can easily find it out if we know the probability of failure of the individual system, and if we can identify, okay, if the system is in series, then okay, this is the way how we can find out the total probability of success or probability of survival of the whole system. So it's nothing but you can easily recall or you can easily remember these formulas. Like if a series system or a parallel system, like we have talked about the series system, and if the parallel system, like if the elements are in parallel system, what we actually know from our past experience, that if one of the element survives, then we can say okay, my whole structure, we cannot say that the whole structure will fail. That means here the complements, that means the probability of survival of the system, we can say 1 minus probability of failure of individual component. And if some events associate events, like these events I am talking about, like uh, corresponding to the failure. Like if we have it's sort of how we can correlate these things. Like if we have some element, and that element level, if we have some probability of failure, and that probability of failure is associated with some event, that means that particular, that gx we are forming using that events, like if we consider that failure according to that you know mm, flexural strength. So that flexural strength failure, if we use that thing, then like here we don't go deep into that. I also frankly don't go into deep into that, but still for I have added these things just because of like this kind of small type of questions may come here, like how we can find it out for a building. If we can identify, okay, this is in parallel, and if I can identify, okay, the probability of failure for the, say for example, probability of failure of buckling failure of the column, if we are considering this, so if I can work out, okay, the probability of first column, probability of failure of the first column is like pf1 is 0.1 or these things, and we can find out all the probabilities associated with the individual column. And if we can identify, okay, this system is in parallel, then we can say, okay, probability of survival of the whole system is nothing but 1 minus multiplication of probability of failure of the system. So here like we have four column, so four column is associated, like pf1 is probability of failure of first column is 0.1, probability of failure of second and third column is 0.3, and probability of fourth column is 0.4. So the probability of total system is nothing but 1 minus multiplication of the probability of failure of the each columns. Now if we have the mixed system, how we can work out these things? So first we need to identify in a mixed system which systems are in series and which system are in parallel. So first we need to find it out, then we can uh, simplify this system as the series system. And first we need to find out the probability of uh, that means probability of survival of the first system, probability of survival of the second system, and we can then add them up. That means nothing but probability of the first system multiplied by probability of second system, and that will give the probability, total probability of survival of the mixed system. So here we can see we have total 4 elements. 2 elements are in series, 2 elements are in parallel. So we can directly replace by S1 and S2. That means S1 contain these two 1 and 2 system which are in series. So first two system series. So we can find out the probability of success for this, and that will be nothing but 1 minus probability of failure of the first system, that 1, probability of failure of the second system. And then for this second case, which where 3 and 4 are in parallel, for this case again we work out that what should be the probability of success of this thing, and then again we add them, actually not add them, we multiply them up, and we get the ultimate probability of failure. Like here we can see that probability of failure of the mixed system pf1 and pf2 is given as this, and pf3 and pf4 are given. So pf1 1 and 2 are in series. So here we can see that S1 is a series system. So PS1 will nothing but, here two system will be there. So 1 minus PF1 and 1 minus PF2. So if you calculate these things, you will get the value. And for the second system, they are in parallel. So that will nothing but that PSS2 will give 1 minus PF3 and PF4. So 0.94, and ultimately the probability of survival of the total system will be probability of E1. E1, that means that probability associated with survival of the system multiplied by probability associated with the second system which is in parallel, and ultimately you will get the probability of survival of the whole system. Now this actually give us some idea about how we can figure it out. If we have some local level of probability of failure, how we can extend to this information to the global level of the probability of failure or probability of survival of the systems. And there are different kind of global level probability analysis. Like in simulation based technique, we have seen that if we have whole structure, and for a particular mode or particular mode of failure, we can easily figure it out how we can calculate the probability of failure. Like we first need to figure it out what should be my limit state function based on my criteria. If I am looking for the maximum deflection, if I am looking for the strength criteria a or any other thing, like for the whole structure, 12-story structure, we have seen that, okay, in the top mode what should be the maximum deflection due to my loads. We have identified some random variables based on that load, and we generated different samples of these loads, or different kind of random variable may be there. We need to generate all samples for this all random variables, and then we need to find out one by one what should be the allowable or maximum deflection level. Allowable we will find out, or we can find out from the model provision or from your technical specifications, in which project you are working with. From there you will get the allowable thing. And for the maximum deflection, you need to run your model again and again using the generated random variable, and you need to look for the total probability of failure. And if gradient based form, if we solve in element level, here there are three approach. Like if my system is in series, how we can figure it out, what should be the probability of survival of the system, what should be the probability of survival of the system if it is in series, or if it is in parallel, or if it is in mix. So in mixed system is nothing but we need to identify which elements are in series. Then for the series system, we need to first find out the probability of success of the series system. Then we need to find out the probability of success of the parallel system. Then for the overall system, it's just we need to multiply these two probabilities, we will get the probability of success of the whole system. And once we have the probability of success of the whole system, 1 minus that will give us the probability of failure of the whole system. So that is the initial or basic concept of the how we can work out from the local level to the global level. Like in FEM, what we generally do, we solve the local level things first, then we assemble all the local things to get the global. Like stiffness, if I am talking about stiffness, we first figure out the stiffness in the local level, then we assemble all the stiffness metrics to get the global stiffness metrics. And different kind of things like stiffness, if we get the stiffness metrics for the mass and all these things, we can easily figure it out. Okay, so that's like a quick revision of the things. If you go through that lectures, you will find out in details. But quite frankly, from this module you will not get any kind of questions in your final examination, except like here, this kind of question: probability of failure of the mixed system. What will be the probability of failure of mixed system if the probability of failure of the individual systems are given? And also in the question, it will be identified if it is in series or if it is in parallel. Okay, so there, like, these are all research level things. If you need to work out with different kind of things, uh, or precisely this kind of parallel or series system, we can assemble for this our system. How we can assemble it, quite frankly I also don't know how we can do it. But for this course purpose, the probability of series and parallel systems, how we can identify it, how we can go with it, we can figure it out. But quite frankly, look at this structure and tell me, this building, this is Nehu building, tell me how we can figure it out for all the columns which are in parallel and which are in series. So I'm not telling that we cannot go with that approach, like we can separate it out in series and parallel system, then we identify the mixed system and overall work out the what would be the probability of failure of the whole total system. And you know to be honest, to tell is the mixed system reliability or the probability of survival of the system will same as if I am going with the simulation based technique. So I also didn't figure it out or solve this system. So if we need to solve this system, we first need to go with a plan, all the details, and then figure it out which are in parallel, which are in series. Then we need to figure it out. With this example, we can take it as like a task and we can solve it, but we don't have that much time to solve it. But if someone is interested, they can do this kind of things. Like we can easily figure it out, the local level things. That means for the beam, say for example we are talking about flexor, and we need to figure it out what should be the probability of failure for a certain load with respect to the flexural strength. Okay, so for all the beams we can find it out. Okay, what should be the probability of failure of each beam? Like the same size and same dimension beam, same length beam will have same kind of probability of failure. And if once we have total probability of failure, then we need to find it out. Okay, total what should be the total probability of failure if all the beams are in series or parallel. So this kind of a thing is like an exercise. We can give it to like some BTP projects, or we can also figure it out, is this kind of approach really worked or not. I quite frankly search for the examples if someone has already done this kind of exercise or not, but I haven't find out for a whole total system, like actual building or actual things in books also. These kind of things are not given, so we can take up this and we can solve it, but for now, okay, leave it and we will focus to our assignments. Okay, so let's go to the 12th week assignments. Like this I'm going rapidly, like this series and parallel system, what should we discuss? If we have a series system, we know, okay, in series, one of the element if fail, then okay, whole system will fail. So whole system will fail, we can multiply, or we can get the probability of success is nothing but 1 minus probability of failure of individual component and multiply them up. And if we have the parallel system, what we need to do, just 1 minus probability of failure of the system. That means in series we can ensure that if one of the element fail, rest of the structure will survive until all the element will fail. Like until all the column will fail, I cannot say the element will fail. But this kind of things is like sort of hypothetical thing. One, if one of the element will fail, we will not consider this building as a safe building. Will you go to the building if one of the element will fail? But my reliability will say, okay, no, my system will sustain. So we need to figure it out, or further, if someone want to go deep into it, they can really work some examples and check whether this kind of things actually align with the simulation based technique or not. So that's all, we will not spend more time. Let's quickly solve the week 12 assignment. Like you need to submit the week 12 assignments. So first thing here, tutorial 1, it's says a random variable follows normal distribution, find out the value of k1 k2 coefficient of the fourth moment standard distribution. So k1 is 1 and k2 is 0, and k3 0 again, k4 3. So k1 and k2 will be 1 and 0. Now here, okay, we have two systems. In two systems, we have in element level 4 elements, 1 2 3 4. So first 1 2 are in series, in parallel, and 2 3 3 4 are in series. So what will be the reliability of the total system? So reliability, that means we need to find out what should be the probability of survival of the system. That means first we need to find out what should be the probability of survival of this 1 and 2 for S1. These are in parallel, and for 3 and 4 they are in series. So for series system also we need to find out the probability of success of S2. Then once we get the probability of success of S1 and probability of success of S2, what we can do is like we can just multiply these two probability and we get the reliability of this whole system. So here, look, calculate the reliability of the mixed system as shown in the figure. The failure probability of each component are given, like pf1 is 0.15, pf2 0.2, pf3 0.1, pf4 0.15. So first two systems are in parallel. So for parallel system, the survival of this system will nothing but 1 minus probability of failure of the element 1, failure of element 2. So 1 minus probability of failure of the first component multiplied by probability of failure of second component. That will give us like 0.97. And the for second system, these are in series. So probability of survival of the second system will nothing but 1 minus probability of failure of the third element multiplied by 1 minus probability of the fourth element. And that will comes as 0.765. And the total, the mixed system, the probability of mixed system will nothing but probability of survival of the first system multiplied by probability of survival of the second system, and that will give us, okay, this is the probability of success of the whole system, 0.742, and probability of failure 1 minus this will give us the probability of failure of the whole system. Okay, so just for the basic concept, I think you have the basic idea. If we have parallel and series system, how we can get And if we know the local level probability of failures, how we can get the probability of success or probability of survival of the whole system, right? So if there is any kind of questions associated or linked to this parallel and series system, I hope you can work out, right? It's like I have went like bullet train, but still we need to solve different kind of questions. We have a lot of questions today, so I hope this
Yeah,
thing.
it's very clear.
Yeah, so let's go to the next question. It's like for the upper bounds and lower bounds. Okay, for the failure probabilities, for the you know here failure probabilities of the three systems are given: pf1, pf2, and pf3. Now for the upper bound, what we need to do, you need to add all the probabilities. This will give us the probabilities of the upper bound. And for the simple bound, it's like what should be the probability of failure. That means maximum of these three things. So for the upper bound, we will have like add three probabilities. So we will have 12 point that. And for the simple bound, lower bound, so maximum of PF1, that will give like 6.25 into 10 to the power minus 3. So these are like upper and lower bound if we have different kind of probabilities in the local level. Now find out the coefficient value for Gram-Carney series of standard weight. Okay, we haven't go through that series. So actually, for these things, B1 and B3 will be minus half and 0. So you just go through that video. I haven't add these slides. Okay. So this the answer will be like minus half and 0. Okay. Here some short question. Find out the correct transform technique for non-normal variable to standard normal variable if a standard normal variable is given. Okay, for the in your lecture video, like I forgot which slide, but three or fourth lecture sir has already explained for the these two standard normal and for these two log normal and exponential distribution. So the a for the log normal transformation this, and for exponential distribution the transformation function will be this. Okay, and this kind of question will not come. Just for your assignments, uh, submit these answers. Now find out the Hermite polynomials h2 and h3 for the second order Hermites of the differential equation is given at that. So what will be h2 and what will be h2 and h3? So h2 and h3 will be nothing but your x cube minus 3x, and the detailed solution I haven't added. Okay, so x cube minus 3x and d x square minus 1. Okay, I will come to it later. Okay, later on, but the answers will be b and d. And we have some more questions like 12th assignment. Okay, which of the following is used for subset simulation? Subset simulation, we have not talked about subset simulation. If you are interested in subset simulation, just mail me. I will give the codes of the subset simulation. Subset simulation actually very easy thing. Okay, the Metropolis algorithm actually used for the subset simulation. So the Metropolis algorithm will be the correct answer. Okay, which one is the most efficient technique to handle the system with a small probability of failure or large dimension or both? It's the subset simulation. Okay, precisely the subset simulation. The subset simulation actually very useful tool, but for the we don't have that much of time. If you want to know about the subset simulation, I can give you the course. And even the third moment based approach, we have figured out that third moment based approach, and we develop these codes for these systems. Like for the frame, this frame problem actually given to this paper, uh, but we actually have coded it. So if you want it, just mail me. I will give it that code for the fourth moment based approach. But personally, I don't like this kind of representation because I have tried with this frame problem, then this double reinforced beam problem. Okay, this for these two problem, it gives the close result with form and MCS. But when I try with the nonlinear problem, it just failed. It's failed terribly. It's failed. Okay, but you can go into the codes. I will upload the codes. Okay, for the fourth moment based representation. But for for me, like I don't like this approach. Okay, then If you want them, I will upload the codes, no problem. Here also for the fourth moment based approach, if you go to the lecture 32, you will find it out what should be the L1, L2, K1, K2 coefficient. So it's nothing but this for the this thing B and C will be the correct answer. That means what select the correct statement about the fourth moment. Okay, the proposed standardized moment. Yeah. So this is the function, the limit state function they propose. So B. And what is the limitations? The limitations is like this. That means above this range, if my fourth moment, the fourth moment is nothing but the kurtosis standard normal distribution, the kurtosis value is 3. And if the kurtosis value is 3, this fourth moment based approach will give the infinity result. That means they will terribly fail. So this is actually the limitations of this fourth moment based approach. So valid when this alpha 4x is greater than 7 plus third moment square by 3. That means in a way they limit the fourth central moment below 3. That's all. If you go to that slide, you will find it out the detail about the fourth moment based approach. Okay, now come to our discussions like what should be or what kind of questions may come in the final examination. Okay, and one more thing, I tell or I told you that I will show or I will share the code of this portal frame, right? And how we can solve using uh, Monte Carlo simulations or the explicit or the form, the implicit form of form. That means first order reliability analysis also we can solve it. So if we have time, I will show the code how we can actually link uh, MATLAB in batch mode to the mechanical APDL to solve this kind of problems. If we have our model ready in mechanical APDL or SAP, how we can use the MATLAB in batch mode to find out the del in each iteration. So this is the, if we have time, I will explain it to you or I will directly upload the codes. You just go through it and the code will be the implicit form and MCS. These two things I will upload it. You, if you go through the code, it's self-explanatory. Just you need to install, you need to have the mechanical APDL and MATLAB in your system. So quickly go to our main discussion, like which kind of questions may come to our final examinations. Okay, so like week 12, we haven't spent that much of time. We just went like bullet train. Okay. I hope you can figure it out, or all the questions I have discussed, you just put it uh, in your assignments and get it done. Like now, first thing, the discussion. Yeah. So in your final exam, you will have 40 multiple choice of question, like rapid fire type of questions, 1 marks question. Okay, and all the questions, more than 90% of the questions will come from your assignments. Multiple choice question, that means 1 marks of questions. Like I will show you how which kind of questions. Now you will have numerical and MSQ type of questions, 15, 2 marks. Here, for the MSQ type of questions, you need to pay more attention. Like 2 or 3 options may correct and actually will correct. Okay, so you need to focus which kind or which options are actually the correct answer of this question. And you have 10 questions of 3 marks. And I can tell you, like if you solve the questions up to week 5, generally week 5 and week 11, up to week 5 and week 11 questions are the most important questions. And I can assure you, like if you solve all the assignments and all the problems I have given here, you can solve more than 95 of more than 9, not 95, 99% of the questions. I cannot directly, you know, discuss the direct questions, but these questions will come to your, this kind of questions even the data will not data will be same in your questions. Like first, in a multiple type of questions, which kind of questions will come in assignments 1? We have seen that probability of failure, and that theory of probability, random variables, moment of distribution. From here, okay, from now we will go slow. So we have 40 multiple choice of questions. Maximum you need 20 minutes to solve it. Okay. uh how much time duration you have for the exam? 2 hours, right?
Yeah, usually it's 2 hours.
2 hours. Okay, so in 2 hours, first go with this multiple choice of questions. It will take hardly 20 minutes to solve, hardly 20 minutes to solve. Like all 12 assignments, you have some multiple choice of questions, three or four multiple choice of questions, right? So from that multiple choice of question, mostly the multiple choice of questions will come from your assignments itself. We will go into it. Now we need to focus on the numerical and MSQ type questions and 3 marks of question. Now the big question is here, which from where these 3 marks of question will come? From the first 5 assignments, from the first 5 assignments and week 11 assignments, the partial safety factors. Not I'm talking about optimal safety factors. You don't need to go or you need to don't need to remember the optimal safety factors, how we are optimize these things. Just for the partial safety factors, like partial safety factors, you have partial safety factors with mean value, you have partial safety factors with the nominal values. All these values will be given in the tabulated format. And one more thing, all the questions in assignments you have seen, or you can also find it out, all the questions which can be solved using pen and paper, this type of question will come to your final examination. Like for week 1, in week 1 assignments, first what do you need to find it out here? If like let me, from PDF and PMF, mostly from PMF, one question will come here. So the values will given for a discrete random variable. Now you need to find it out what should be the PMF value. So you can easily find it out. If you have the probability of failure, you just need to add them up. Okay. Now here one more question we will solve here. Like here, look, we have 0 1 2 3. Already we have solved this question, you know, just go through it. And the options will be like, what should be the f of x within that range? The range, they will ask the range. Here for all the range this is given. Now if this question is given and ask what should be f x of x with respect to 3, that means this. So what will be that? For less than equals to 3, you need to figure it out, it 1. Just as simple as that. You don't need to find out or write all these things, but this table will be given, this kind of table will be given. What should be the probability of failure with respect to, or less than equals to 1, less than equals to 2, or less than equals to 3? That means you need to add all the probabilities up to that point, right? So one kind of question. Second, one question will come from this, your, for the continuous random variable, the PDF will be given, the probability density function will be given. Over the range, some constant will be there, you need to find out the value of the constant. Now what is the approach to solve this question? It's nothing but, we know, for the whole domain, the probability of failure, uh, the for the whole domain, my PDF f x of x dx will be 1. So if this kind of question is given, like f(x) of x over the range 0 to 1 given as ax, over the range 1 to 2 given as a, over the range 2 to 3 given as 3. So you, what you need to do, you need to integrate all the things and equate to 1, because we know the area under this PDF is always 1. I am here drawing the normal distribution, but for all the distribution, the PDF over the range, it will be 1. So you need to figure it out, what should be the constant. Now once you have identified the constant, now for a range like here for 1.5, what should be the probability of failure is equal less than equals to 1. That means you need to add, that means you need to just integrate up to that point. Like here if we have 1.5 value, what should be the probability of failure less than equals to that value. That means you need to calculate the area under this curve. That means you just need to integrate up to that point. Okay, if this is not the standard normal variate, if standard normal variate will be there, that means you just figure it out phi of that point x minus mu. Clear? So this kind of question, 3 marks question will come where you need to find out the value of this constant a, and you need to figure it out for some interval or some point what should be the probability of failure. Clear? So from this module, these two kind of question, and one more question like here again this question is given like what should be the value of this constant. How we can figure it out? The that PDF is given as k multiplied by x minus 1 to minus x within that range and otherwise 0. So what will be the value of k? That means what we need to figure it out, that minus infinity to infinity, just integrate the PDF value equate to 1. Simple integration, the simple integration will be given, which can be solved using pen and paper within 2 or 3 minutes or within 2 minutes only. So k will be 6. Clear? So this kind of one question will surely come. Okay, now let's go to the second kind of question. One more thing, you need to recall 2 or 3 distribution where the parameter will be asked. Like for the type 1 largest distribution, if the mean value and the standard deviation value are given, what should be the parameter for the type 1 largest distribution? Okay, so in a way you need to figure it out, or you need to remember these two formulas. What is my mu, what is my sigma for this distribution? So 2 or 3 distribution I will tell. First, type 1 exponential. Where is exponential? And log normal 3. So for log normal, x tilde is nothing but this, and sigma ln square is nothing but this. So your del value, that means the coefficient of variation value will be given, and the mu value will be given. And the question in question, it will be asked what should be the parameter with respect to the log normal distribution. So log normal, type 1 and uniform. For uniform, it's nothing but 1 by lambda here, and type 1 smallest, actually the type 1 smallest is very important, mu x and sigma x, these two. And exponential, here is the exponential, here exponential, mu x is nothing but 1 by lambda and sigma x is 1 by lambda square, and the distribution is lambda e to the power minus lambda x. Okay, like this kind of question will come. So for distribution you need to recall first the exponential, type 1, type 1 largest, type 1 smallest, and the log normal distribution. Clear? The 4 distribution associated with the parameter associated with that 4 distribution you need to recall. You need to remember. But and third type of question for the standard normal variates. Here the standard normal table will be given to you, like for the range. You already have seen in your assignments, like here like phi and z values will be given corresponding to that values. What you need to do, all these things will be given, mu, sigma. Like for this M20 grade of concrete, it follows normal distribution with distribution mu is 31.57 and sigma is 4.32. What will be the probability of getting a strength less than equals to its design value? The design value is 25. So here what you need to do, just phi of x minus x, that means the desired value here, that is the 25. This is the mean, this is the standard deviation. So phi of this and this value, phi of this value you will get it from the standard normal table. So sometimes you need to interpolate it, some linear interpolation, but I think the questions, in the questions, no need to interpolate the phi value to get the answers, but this kind of questions you will see. So from the first 2 modules you will get more than 60% of the questions. Okay, first 3 modules, more precisely first 3 modules. uh, I will come to it. I'll come to it. So three type of questions from here you need to recall. Okay. For the log normal distributions also you can find it out. Similar kind of things. Phi value. Just just recall this final expression for normal and log normal. So two type of questions. One, for the normal distribution is nothing but phi of x minus mu by sigma. For log normal distribution, phi of ln x tilde by your uh, ln, that sigma ln z. That means you need to find out the x tilde value and sigma ln z. That means a few times back I already said you, like, for this distribution you need to recall the parameters. Okay. And exponential distribution 3. What is the exponential distribution? I need to figure out the exponential distribution. That rainfall question we have already solved now. That question, just go through it. And one more thing here. Yes, this kind of question. What should be the mean and variance? This is nothing but the question from the variance of algebra. Like here, how we need to find out the mean and standard deviation for this kind of questions is nothing but it's a linear system. So here the total load for a column is given. This is your limit state function is given as S, dead load, live load, wind load, and dead load follows normal distribution, live load follows normal distribution, again wind load follows normal distribution. Find out the mean and standard deviation. That it will be the 3 marks question. How you can figure it out? The mean will be nothing but it's an linear equation. So mu of d, mu of l, mu of w, just add all the mean values. What will be the variance? Is nothing but sigma square l, sigma square d, sigma square w, and you will find out the standard deviation up to this. Now once you have find out these two, you can easily find out the probability of failure of this thing. That means all the things what we need to recall is actually linked to each other. Okay. For distribution, four kind of failure. For distribution, out of these four, two distributions are very much important: normal, log normal, then your exponential 3. And for the type 1 largest, you need to find out the parameters. Okay. Three questions, three type of questions. Okay. Now this is similar kind of question. It's an nonlinear equation, so you also find it, you can find it out mu and delta according to it. Here this question. Now look, here we have a limit state function s is equals to m by z p by a, m p a. The distributions of these things are given along with the parameters. Now what should be the variance and mean of these things? So mean is nothing but mu m by mu z, mu p by a, because a is your deterministic quantity. So we can easily find out the value of mean. And what should be the sigma square value? It's nothing but 1 by mu square. That means 1 by mu z square into sigma m square plus. That means you need to find out the derivatives of these things and add them up, and you will get the final expression. So variance of these things, when we have nonlinear function, we just need to uh, we need to get the derivative with respect to the random variable, and put this in this equation. So when I is equals to j, you will get in the square term. So this problem, just recall this problem. Already we have discussed this problem in week 1, during the week 1 assignments, or week 1 assignment solving session. Now one more thing, these are all same kind of things. Mean value, what will be the mean value? If my limit state is given, what should be the mean value? This will be my mean value. What should be the variance? Nothing but del mr by del b square into sigma b square. That means you need to find out the derivative with respect to the random variable and multiplied with respect to the sigma square of this particular random variable. That's all. And one more question here. What should be the, not this, what should be the joint distribution and the marginal distribution? If the joint distribution is given, what should be the marginal distribution? Now if we have the joint distribution, how we can find out the marginal distribution? Tell me. We need to integrate it with respect to the other dimension. Yes or no? I'm going little fast, but you can correlate it. Like if we have the joint density function or joint distribution function, say if you have the joint uh, PDF JPDF fxy is equals to some values. Now if you ask to find out what should be the marginal distribution with respect to x, so if y of y will nothing but you need to integrate within that range with respect to the other dimension, that means f xy dx, and you will get the value. So the given from the given joint distribution you need to find out the marginals. Great. Okay, now from the week 2, so from week 1, which kind of questions you need to recall or you need to practice are these. If you practice these questions already we have solved, you can solve 100% of the questions given from the week 1, and week 1, week 2, week 3 have the most weightage. Okay, clear which kind of questions you need to practice from week 1?
Yes.
Okay, great. So move to week 2. So in week 2 we have moment generating function, we have method of moment, and maximum likelihood function. Now from the goodness of fish like chi-square and case test, you will have one or two MCQ type of question. Okay, and most of the question, one question will come from the moment generating function, because in our assignments the weightage regarding moment generating function is given mostly. So I will show you some example. Like here we need to find out the moment generating function for the discrete random variable. So here what we need to do, recall how we can find out the moment generating function. Nothing but moment generating function is e expectation of e to the power xs. So if we have the PDF with our with our side, so e to the power xs we can easily find it out, but this kind of bigger expression will not given to you, where you need to find out the or you need to solve the integration. But this question, if this question is given, how much time you will need to solve it, tell me? Like 2 minutes. So you can expect one question from moment generating function. Okay. So just go through the moment generating function of questions, whatever we have discussed during that week 2, like this question, and we have again this type of questions. If we have discrete random variable, the PMF is given for x equals to 1, it's 1 by 4, for x equals to 3, 3 by 4. So the moment generating function of x is nothing but summation of 1 to not infinity. Here we have only two values, so we need to figure it out two values. So e to the power s corresponding to 1, that means e to the power s 1 by 4, the value PMF value is given as 1 by 4, e to the power 3x, because corresponding to x equals to 3 we have 3 by 4 as our PMF. So what you need to do, this is our moment generating function, and from the moment generating function if we ask to find out what will be the first moment, what you need to do, you need to get the first derivative of the moment generating function with respect to s, and you will get the first moment. So this will be your first moment and this will be your second moment. So first moment and second moment, if you figure it out, you will get in the values. So this kind of question, like where the moment generating function or the PMF is given with respect to some discrete values, this kind of question you can expect in your final exam. This, so moment generating function, how we can get the moment generating function, it's nothing but you need to integrate e to the power sx with respect to the PDF. If you have the continuous random variable, if you have the discrete random variable, you just add them, add the all the e to the power sx value with the particular PMF value, whatever given to you. Right? Now once you have the first moment, here one more thing I must say, like the central moment and the moment about origin. If you ask the moment about origin, then here the moments after getting the derivatives of the moment generating functions, you will get the moment about origin, right? Now if you ask for the central moments, what you need to do, These are the moments about the origin. The central moments, first central moment is mean, or the first central moment is 0? Tell me. First central moment is, what is the first central moment? 0.
0.
The second central moment is variance. Third central moment is skewness. So skewness will not ask to you. Up to the variance you will ask. So for this question, let's solve this question. Okay. Here the px is given. So moment generating function. This is your moment generating function. Now the derivative with respect to the moment generating function, if we derive it with respect to s, simple derivation, we can get this. Now this s equals to 0 will give us the first moment about the origin. Okay. And second derivation will give us the second moment about the origin. So second moment of the random variable is 7. Now the second central moment will be the variance. That means this is nothing but your mean square, e of x square, mean square value. Now once you have mean square value from the variance of algebra, we know the variance of x or variance of the random variable x will nothing but e of x square, that means mean square value minus mean square, right? From the variance of algebra we have already proved these things. So just recall these things or these catches, and you will have one question from this. So this kind of complex question will not come, but still you can figure it out if this type of question is given. But I can assure you this will not come. But this kind of, where the discrete random variable will given, or simple form of the continuous random variable will given. Same for here for this question, the pdf, here this is the random variable, continuous random variable. So the pdf is given. What you need to do, first you need to find out the moment generating function. What you need to do, you just integrate this function with respect to this. So minus infinity to infinity, if you work it out, you will get this will be your moment generating function. Now what should be the first moment of x using moment generating function? What should be the first moment of x? How we can find out first moment of x using moment generating function? First moment of x, that means the question asks you the first moment about the origin, because from the moment generating function, the moments we are getting, these moment, all the moments are the moments with respect to the origin. And for mean, the central moment, we need to go like e of x minus mu variance. What was the expression for the variance? Recall, e of x minus mu the whole square. So first moment, if we figure it out, e of x minus mu, so obviously the first moment e of mu minus mu will be 0. The second moment or second central moment will be x, e of x minus mu whole square. That means give us the variance. And for variance algebra, we know the variance of x is nothing but e of x square. That means mean square minus mean. That means first moment, first moment about the origin, that square. So once you have the moment generating function, just derive or get the derivative with respect to s, equate it, or s at s equals to 0, you will get the first moment about the origin. Like here, e of x, that means the first moment of the random variable x will nothing but ds of this moment generating function at s equals to 0. So if we figure it out, you will get the first moment about the origin will be 0.444. And what will be the second central moment or second moment about the origin? The second question asks compute the second moment using the moment generating function. That means second moment about the origin. That means you just need to derive the or get the derivative, second derivative of the moment generating function with respect to s, and at s equals to 0 you will get the second moment about the origin. So here you can see the second moment, here the second derivative of the moment generating function with respect to s, this. Now at s equals to 0, if you put s equals to 0, you will get this. So this is nothing but the second moment about the origin. Second moment about the origin. Now, once we have the second moment about the origin, you can easily find out the second central moment. That means nothing but the variance. Second central moment is variance. Variance is nothing but from the variance of algebra e of x square minus e of x the whole square. So we have the e of x, we have e of x square, that means mean square value, mean and mean square value, and we can find out the second central moment. So first central moment is always 0, second central moment is the variance, third central moment is your skewness, and fourth central moment is kurtosis. So mean is always the moment about first moment about the origin. Okay. Now here you can have 1 marks question or 2 marks question from the bias and unbiased estimation. Like if you have estimator, the estimator will be given to you, or the sample estimator will given to you. Now in a question will ask, okay, tell me which one will be the unbiased estimate of the mean or unbiased estimate of the uh, that estimator. Okay, so this kind of question, 1 or 2 marks question may come. Like here already you have solved z1 z2 z3. Like bias, why we can say, if expectation of the estimator, if it is equal to the population parameter which we are looking at, if these are same, then we can say okay, this is my unbiased estimate. If these two are not same, that means the estimation of the estimator, expectation of the estimator is not equals to the parameter or the sample parameter, then we can say okay, this is the bias estimator. So here we can say like here two estimator of z1 z2 and up to z9 is given, theta 1 and theta 2. We need to find out which one is the unbiased estimate of mean. So what do we need to do? So expectation of that phi hat, phi 1 hat, we need to find it out. Expectation of phi 1 hat is nothing but expectation of x1 x2 up to 9. So here all the values are given here. So 1 by 8 7 mu, we have like 7 mu, so 7 by 8 mu. And for so that means e of phi 1 is not equals to mu. That means it's the unbiased estimate of this phi this mu. And for the
Hello.
second case, yeah,
Why is it 7 mil? Because if you check, it's from 1 to 9.
like here for the question it is given 1 to 9. like
Yes.
like for the sample mean and for the sample covariance, for the standard deviation, we have seen like here what is the unbiased estimate. Like when we derive this thing, if you go back and see these lectures or the interaction session, you can see that uh, variance, when we estimate the sample mean and sample variance of some um, mm, distribution, so we can see the sample variance 1 by n minus 1 will give us the
Yes.
unbiased estimate. Or here for the question
Yes.
itself, it is actually given for up to 9. That's all. Here for the question, actually it is given E1, E2, and E3, E of x1, E of x2, and E of x3. You just need to sum it up here. Up to 9 is given. That means E of x1 plus E of x2, all are mu. Like all the values are given. So this kind of actually values will be given here. So for the second case, like 6 mu minus mu minus mu minus mu. For the first case, we have like, okay, this is 7, not 9. Thank you. This is 7. Yeah, yeah, Bob.
Yes.
Yeah,
Thank you.
this is 7. Yeah, sorry. Yeah, this is 7. Yeah, 9. Yeah, if it is 9, then also it will be the bias estimate, right? But yeah, for this question that must be 7. Yeah, so for 7 you have just mu, individual mu's, you just add them up. And uh, here we have like, I'll correct it, it's 7. That means similar type of question, the estimator will given to you, the values will given. Like here you just for the mean, you just need to add them up. So you have 7 by 8 mu. So it's not giving us as mu. So second case, we are giving E of phi 2 as mu. That means, okay, this is my unbiased estimate of the mean. And also just recall this, for the sample mean and sample covariance, what should be my unbiased estimated. So for the sample covariance, the 1 by n minus 1 summation of x minus mu whole square for each sample, that will give us the unbiased estimate. Okay, 1 marks question. And from the moment of estimate, here it's nothing but you just add them up, you will not get that. Now the one not one, you will get 2 or 3 questions from the maximum likelihood estimate. 1 marks question you will have from maximum likelihood estimate. Again you will have 3 marks question from the maximum likelihood estimate. Okay, so here what you need to careful about the questions, you just read whether you are asked to find out the log likelihood function or the likelihood function. Okay, in one question it may ask like what should be the likelihood function. For the likelihood function, you just need to sum them up and find out the thing. Here you can see. And for log likelihood function, you need to add the log on the both side. So from here, likelihood and log likelihood function, you will have 2 to 3 questions. 2 questions, 1 marks, and I think 1 2 marks questions may come from this topic. Okay, so already we have figured out different kind of questions here, and all the questions given to your assignments, you just go through them one by one. And already this kind of questions are given, like what should be the likelihood function, what should be the log likelihood function, very simple type of questions. Okay, and all the answers will be given. You don't need to find out the parameters, but you will be asked what should be the expression for the likelihood and log likelihood estimate. Likelihood and log likelihood estimate. Clear? Likelihood and log likelihood estimate. And be careful. In options, the likelihood and log likelihood, both the correct answer will be given. So be careful with the answers. Okay, so from the log likelihood function, you can expect 2 or 3 questions. Simple type of questions. What should be the likelihood function, what should be the log likelihood function, that's all. Now from the week 3, yeah, you will have most of the 3 marks question. First, most of the 3 marks question will come from the week 1, like what should be the mean variance for a given system, what should be the probability of failure up to this point, what should be the k value for these things. So 2 or 3 questions you can directly expect from the first module, and rest of the things here from the MVFOSM and the definition of corner reliability. That means first you need to figure it out, what should be my mu and what should be my sigma of the limit state function, and what should be the beta. So for this question, like here, you can easily figure it out, what should be the mean and standard deviation of the limit state function. So the limit state function is given in this format, and the format also will be given to you, like which format you need to follow. Like here, if I change the format 1 minus d by c, the estimate of beta will change. That actually lead to the lack of invariance problem, right? So this kind of question, 3 marks question, will obviously come. I think this kind of question will come. Like the axial load carrying capacity of column is given, the capacity is given, the demand is given, the limit state is given. So what should be the reliability index for this problem, and you need to enter the range of this value. Okay, so for this problem you have the limit state function c minus d. So what will be the mu g, is nothing but mu c minus mu d. Already we have the parameters corresponding to the distribution, so I can easily find it out, what should be my mu g, what should be my sigma g. It's a linear function, so it's nothing but sigma c square by sigma d square. So I can get the standard deviation. Once I have the mean and standard deviation using the Cornell definition, it's nothing but mu g by sigma g. Okay, now further if asked like what will be the probability of failure, so obviously in a tabular form the phi value will be given, but up to that will not go up to that. So up to this what will be the beta value corresponding to that limited function? This kind of question will ask. Okay, so this big question you just don't need to go with, like simple kind of limit state will given, where you can solve within 2 or 3 minutes. Great. This question, yeah, this also one of the important question. Already we have discussed these things, like moment of resistance is given. What will be the mu r? Is nothing but 1.138 0.138 fck bd square. So mu of fck, mu of b, mu of d. You need to find out which are my random variables. So b is my random variable, normal random variable with mean mu, mean 400 and standard deviation 4. D also my random variables, and bending moment is a deterministic quantity. So you can easily find out what should be my mean value. Now to find out the sigma value, what you need to do? First you need to find out the derivative with respect to mr. First derivative with respect to mr of fcb, because my random variable is b and d. So you need to find out the derivatives of the random variables, then sigma at that point, that that del mr, that means my limit state function or this given function with respect to b, that square into sigma b square. Because recall that formula, summation of ij is equals to del mri by del mj by multiplied by this into covariance of this. Now covariance, if there are no correlation coefficient is there, the covariance will become the variance and you will get this formula, right? So this type of question, like you will be given here. Now if asked what should be the reliability index as per the Cornell definition, you can easily find it out, mu mr by sigma mr. So from the Cornell's definition, you will have one kind of questions. Okay, 3 marks question. Here also we have another question, like here the covariance is given. So if covariance of given, you can also find it out what should be the variance, mean and variance, and the corresponding beta. Great. Okay. So beta from reliability index, 3 marks question. Here also just go through these 3 or 4 problems here added, just go through them. Already we have discussed these things. This question also important. Okay, mu, you can find out mu, you can find out sigma, you can find out beta. Now from week 4 we have the form. Now the big question, from first order reliability method, which kind of question may come here? Very simple kind of question will come, like here this kind of question. Your z will be given directly, the gz will be given, your alphas will be given. Calculate the beta for the first iteration, and your limit state will not be this big. It will be simple linear limit state where we just need to find out the beta value. That means what you need to do, already if it is given on the z space, obviously it will be given on the z space, because in x space to z space you need to convert it. So it will take some time. So I think directly the z space limit state equation in z space already given, and in a simple format, like you can easily find out the beta, and beta will have only one equation. You will not have any quadratic equation where you need to solve for beta and you will get 2 or 3 values. You just will get one values. What you need to recall here, that in design points zeta equals to beta into alpha. Already we have seen many times when we have solved using Reckwitz and Reckwitz-Fissler algorithm, right? And already we will have alpha and alpha 2. And another kind of question, like here you can expect what should be my alpha and alpha 2, this kind of questions here. Like say for example, your gz is given is like that. Say for example, your gz is given like this. Say my gz is given is 20 z1 minus 6 z2 plus 220. Now here what will ask, like what will be my calculate the direction cosine of the first random variable. First random variable, that means you need to find out the alpha one. So alpha, what we know, is nothing but minus the gradient, or the gradient of the limit state function in the standard normal phase with respect to that Random variable, that means dz1 divided by gradient of g, that means Euclidean norm of g. And Euclidean norm of g, most of the things your Euclidean norm will be given. If not, you need to find out two derivatives like dg with respect to z1, dg with del g with respect to z2. And Euclidean norm is nothing but your under root of that square plus this square. So once you have this, you can easily find out the alpha 1. And if asked, so what will be the value of alpha 2, you can easily find it out. Is nothing but dg by dz1 Euclidean norm of gz. Great. So this kind of question you may expect. This two, like one where you need to find out the beta, where this kind of limit state is already given, and one type of question where the limit state is given, you need to find out the alpha. Alpha, that means you need to find out the first derivative of the limit state function in the standard normal space with respect to that particular variable. On similarly, if you have two random variables, so you will get two gradients of the limit state function in the standard normal space. You can have the Euclidean norm. You can easily find out the Euclidean norm of this thing, and you can find out the direction cosine. So simple kind of thing you may expect from the first order reliability method. Clear? You don't need to go for the iterations and all these things. Okay. So kernels, from the kernels definition, you may have one question, one 3 marks question, and from form you may have one 3 marks question and one 2 marks question. Clear? Great. This Newton-Raphson iteration you will not have. I think you will not get any kind of question from this kind of thing. Okay, you don't need to remember this, but this type of questions, yeah, this kind of questions also in Z space. Yeah, I almost forget. In Z space, all the values will be given in Z space. Now, find out the final design points. You can find out the final design points because we know how to go from the x space to z space. Z1 is equals to nothing but x1 minus mu x1 by sigma x1, right? So x1 will be nothing but mu x1 plus z1 sigma x1. So let's discuss this problem, this kind of problem. So three kind of question you need to recall. A limit state equation considering two random variable x1 and x2. X1 follows normal distribution, again x2 follows normal distribution. It is solved using form. The final values of the reliability index is given, corresponding direction cosines are given. Find out the design point in the given space, that means x space. You just need to convert the z space into x space. How? What was the expression for it? What was the expression for it? It's nothing but z1 is equals to x1 minus mu x1 divided by sigma x1. That means you need to find out the x1, which will be z1 sigma x1 plus mu x1. Now you need to find out the z1. Z1 is nothing but alpha 1 into beta. Yes or no? Just you need to replace this thing and you will find out the final value of x1 and x2. These three kind of questions, that's all. And from the kernel's definition, what will be the beta? What will be the beta? That means you need to find out the mu g, sigma g, and you need to calculate the beta. And your limit state will be simple linear form of limit state, where you need or don't need to go for the go for the or you don't need to take the pain to get the derivatives. Okay, that's all. This kind of correlated to uncorrelated, you will not have any kind of questions. Now, from the week 5, Recruits and Recruits Fischler algorithm, similar. Like here also, same kind of questions, same kind of questions. So from you may have three questions itself, and from no, from kernels also you have three. That's why I told you up to fifth week of assignments, you if you solve this kind of question, you can solve 70 to 80% of the questions. Like here also beta, similar kind of question. Look at the question here, the limit state is given, you just need to convert it into z space. So directly in your questions, directly the gz will be given, you need to find out the beta. So you can easily find out the beta here. That means all the values will be given, you just need to recall or remember what was my logic to find out these things, and the simple form of limit state will be given. Don't worry, these two this also you can solve. Like don't look at the solution, can you solve it within 3 minutes? This, if this is asked for 3 marks question, although the limit state is bigger here or longer here, but this kind of limit state will not given. Like limit state is given, initial beta is given, initial alpha is given. What will be the beta for the first iteration? For the first iteration, you don't need to solve any quadratic equation, it will be simple linear equation. Okay, so now you have idea how or which kind of questions will come up to this module. Yes or no?
Yeah.
Yeah.
So then log normal distribution, I have already uh, told you. This kind of also question, 1 mark question may come from this, like what should be the equivalent normal. Only for the log normal distribution you just need to recall what should be sorry, what should be the equivalent normal. So for the log normal distribution, what should be the equivalent normal, that equivalent normalization thing, the equation here, mu dot x is equals to x star minus 1 minus ln x star and ln x star, all will, the value will be given, like x star value is given here, the standard deviation and mean is given here. So that means you need to find out the del value first, you need to find out x tilde value, and you can find out the equivalent normal point of particular to this x. So 2 marks question may come, or 1 marks question may come here. If the covariance, that means the del and x tilde is given, the question will be 1 marks. If you need to calculate these two things, you will have 2 marks question. That means in a way, that fourth distribution, what I have told you, that according to that fourth distribution you can solve any questions, right? So this also you just go through it. So it's simple question, and this also only for the log normal distribution, not for the uniform, not for the Gumbel, not for the type 1 distribution, but for the log normal distribution. It's simple expression, x delta 1 minus ln x delta plus uh, ln x star, that means minus ln x star plus ln x tilde. So this kind of question may come, but the thing is, I suppose this question may not, will not come, because ln value you cannot solve using on-screen calculator. I don't think so. Ln thing is there na, on-screen calculator, the ln you can solve na.
Not
I
sure.
think it's there.
Yes, maybe.
You can solve na. So you just go, just recall this expression, what should be the equivalent mean for the log normal distribution. Okay, so this kind of question, 1 marks question, hardly 1 or 2 marks question. If all the values are given, then that question will be 1 marks. If all the values are not given, then this question will be on 2 marks. Like this, calculate the standard normal distribution. Here all the things are given, you just need to find out the equivalent normal parameter, that one for the mean, and this one is for the standard deviation. So these two formulas, so mean formula is x star 1 minus ln x star plus ln x tilde, and for standard deviation is nothing but x star into ln sigma ln x star. So sigma ln x star you can easily find it out using ln into del square plus 1. Yeah, del, that means the coefficient of variation. So these two questions you just recall, or you just go through them. Okay, this kind of question you will not have, because you cannot or you don't need to solve the eigen operations. Now, in Morgenstern and Natam model, you will have just MSQ questions and simple theoretical questions. Like you will not get any kind of numerical questions. But one question I will recommend: just recall this formula. What is the formula to find out the alpha? This means that row value, how we can find out from the alpha value. That means q1 and q2 is given. So this, from this formula, how we can give, how we can find out the row 1 2 value. That means if x1 and x2 marginally normal and exponential distribution, q1 and q2 is given, what should be the correlation coefficient? So q1 and q2 is given, so we know that alpha, mod of alpha is less than equals to 1, and the alpha is nothing but row 1 2 into 4 q1 q2 less than equals to 1. This 4, row 1 2 divided by 4 q1 q2 less than equals to 1. This formula all are given. What will be the row 1 2? That means the correlation coefficient between these two first, and for the 3, these two formula, please recall. That's all. and and 1 marks question associated with that, uh that week 6, all the 1 marks question you should go through them. 1 marks and msq question, related to all the statements, which statement is correct, which statements are correct, which are the correct statements. Okay, that's all. Rest you don't need to remember any kind of transformations, Nattov or Morgenstern. Clear? So from this isoprobabilistic transformation, two thing: first, mcq 1 marks question, msq, that which statement is correct, Morgenstern model and Nattov model, like which one is the robust model, which model is work for the wide range of correlation coefficient, or we know the Nattov model, because the Morgenstern model has limitations like zero point 0.3, the correlation coefficient up to 0.33, we cannot work with the Morgenstern model. These questions, like this 1 mark question, whatever is given to your assignment 6, you just go through them, the 1 mark question and msq question, and along with it these two formulas you need to recall. First, for if we have two random variable, what should be the row 1 2, if q1 and q2 is given, all values will be given, q1 and q2, you just need to find out what should be the row 1 2 value. That means what should be the maximum value of row 1 2, which we can work with that, the Morgenstern model. That's all. Now, from second order reliability. From second order reliability, again, you will have the MSQ type of question. MSQ. I will go to the, week 6, week 7. You have the assignments of week 7. I also have the assignments of week 7. Just wait a minute. Your assignments, actually. The assignments is given to you. The MSQ type of questions. That's all. Like that is the solution, whatever is given to you. So here what you need to recall, all the msq type of question, 2 marks question, which one is the correct statement, right? Which one is the correct statement? Already we have discussed all these things, you know this very well. And one thing I will suggest, like what is the tate model, if a1 a2 and a3 is given, 1 mark question, you can easily find it out, right? That's all, these two kind of questions. And for if there is only one beta and one kappa, so and already phi of beta is given, what will be probability of failure with respect to the Brightung model? You can figure it out, right? Phi of minus beta 1 plus kappa beta, but I think that kind of question will not come. Still, for Tate model, this expression PF2, and for the Brightung model, and for the Tate model, this PF weight is equals to A1, A2 and A3. If A1, A2 and A3 are given, you can easily find out what will be the value corresponding to Tate. But the MSQs, okay, just read them carefully and solve them. What which are, or what which are the correct statements? Okay. And here, if the d vector, what was the d vector for here? Son is nothing but the second derivative vector. So if like the limit state function is given, you just need to find out what will be the second derivative with respect to the standard normal variate, that variables, and you can already find out the d matrix and the terms of the d matrix. So if this kind of question will come, you can figure it out, right? So this kind of small question will come from the SON, and more precisely MSQ weight model A1, A2, A3 for 1 marks, and the derivative D matrix. Here the D matrix also important. D matrix, simple form of limit state will be given. What you need to do, you need to find out the second derivative of this limit state function in the standard normal space with respect to first random variable, second random variable, and which will form your D matrix. Clear? Great. Now move to the week 8 assignment. Like some few questions I have added here, you just go through them. Here, look, for the D matrix I have added one question, you can easily find it out what should be the D matrix, right? That's all. A matrix, you don't need to find it out, because the matrix operation there, you don't need to figure it out what should be the final values. Like the motto is not there to give you like this matrix operation we can easily do, but this will consume time, and it will be problematic to solve during the examination. So this kind of question will not come. But this d matrix, the element of d matrix may come. Okay, some sort of limit state will give 3 marks of question, not 1 or 2 marks of question. 3 marks of question may come from here. Right? Yeah, like which one is the correct statements? Some will give, we already we have discussed these things, so just go through it, you will find out. So msq, one msq 2 marks question, like tate model, if a1 a2 a3 is given, 1 marks question. And if one limited function is given, what should be the element of the d matrix? Like what will be the d11 value, what will be the d12 value? That means d11, it's nothing but the second derivative of the limited function in the standard normal space with respect to the first random variable in the standard normal space. That's all. Just or the derivations will be very simple, you can easily get it. Either it will be 0 or in the cross term you will have some term. That means easily you can find out the derivatives. Great. Now week 8. Here from the Monte Carlo simulations, again that means the simulation based technique, again you will have the MSQ type of question, mostly the MSQ type of question. And here this type of question, if for 3 marks question, if it's 2 marks question will be given, limited will be given, some sample points will be given like 1 2 3, 3 or 4 sample point will be given, what will be the probability of failure? That means what you need to do, and a simple limit state will be given. So using the sample points you need to evaluate the gx, you need to check how many times it fails and how many times it pass. So your probability of failure will be how many times it fails divided by total number of samples. That means easily you can find it out. Clear? And for important sampling and adaptive sampling, you will I think you will not have any kind of numerical type of question, but you may have MSQ type of question, 2 marks of question MSQ. And just recall this formula. Okay, like error and k, all these things are given, you need to find out the n. So n value, simple values will be given, like probability of failure, error, and 95% of the confidence interval. Find out the n value, number of simple. So this equation also you need to recall from this module. This I have added some few questions here, you just go through them. Okay, now from week this is week 8. Now let's go to the week 9. Week 9 also you will have 1 marks and MSQ type of question, mostly the 1 marks question. Let's see the week 9. It's response surface and stochastic response surface, all these things. So you will have MSQ type of question, and very like one or two question may come from here, or less. This is week 8, we don't need week 8, we just need week 9. And from the week 11 you will have 2 or 3 questions. It's very simple. The points will be, I'll go to that. Yeah, so most of the 1 marks question will come from here, like what should be the interval from the Hermite polynomial, you just recall it. So 1 marks question from this module and MSQ question, 1 marks and MSQ question. This formula you should recall. What is the new design point for it? The interpolation formula. But no numerical things will ask, like this kind of MSQ question. MSQ, only MSQ type of question will ask from this module. MSQ and 1 marks of question. 1 marks of question. Okay, you don't need to figure out what should be the polynomial, orthogonal polynomial, all these things you don't recall, or you don't need to recall these things. Here you may ask, like what should be the support point generation scheme for this mu plus minus k sigma. So for this thing, if the mu and this limit state function is given, what should be the points, or how much point we will get here, or what should be the points, 2 points from here. So MSQ type of question may come from here. So MCQ or MSQ, this question you just need to recall. Okay, this and all the MCQ and MSQ question from this module. Week 10, let's go to week 10 quickly. Week 12, you will not get any kind of numerical questions. But that thing, parallel and series, I just forgot. Maybe come from there. So here the roots of the first a polynomial, don't need to recall it. It will not come. This type of question like polynomial chaos expansion, the correct statements like Kosla's point, you don't need to recall. Yeah, this thing, this question number 6. What is the difference between least square and moving least square, weighted least square things? So weighted least square things, you just need to multiply the weight function with respect to your normal least square approach. That means x transpose x inverse, you need to multiply with the limit state function, and for the rest of the thing also you need to multiply it. So this type of question, 1 marks question, all the 1 marks question, this all the 1 marks question and the MSQ question, you just recall all those things from this module. So it is advised that that all modules should be covered. So 1 2 question, 1 marks and 2 marks question may come from this, or mostly the 1 marks question, the MCQ type of question. Okay, now week 11, again in week 11 already we have discussed which kind of question may come. I have added some question here for the week 12. You can easily go through it. Yeah, like 3 marks question, 2 or 3 marks question, mostly the 2 or 3 marks question will come from here. And which kind of, like uh, your limit state function will be given, the random variable will be given, alphas will be given. What you need to find out, you need to find out the x values in the normal space. In the form already I have said, like if alpha, beta and z values are given in the records algorithm, I already told you to recall these things. So you need to convert it into x domain and find out the partial safety factor with respect to mean or with respect to nominal values, whatever we will ask to you. So here the with respect to mean, because the mean values are given to you, so what you need to do, you need to find first convert this into x space. That means the design point is nothing but mu x1 in plus z1 into sigma 1. Z1 is nothing but alpha into beta, alpha 1 into beta. So alpha values are given, all these things. And you can find out the factor of safety, partial factor of safety. Only the partial factor of safety is not optimal factor of safety. So mostly this question first, and here this kind of tabulated format, your mean to nominal values will be given, your design points already given. You just need to find out what will be the mm, uh, factor of safety with respect to mean value with respect to the nominal values. Clear? 1 marks, 2 marks. In 1 marks question, one table will be given and 2 3 question will be asked for 1 marks question. Mean value of this, what will be the nominal value, partial factor of safety with respect to the nominal value, and all these things. Clear? And this LFDR safety checking format. What are the 4 equations for the LFRD safety checking format? What are the 4 equations? So one MSQ question. So this question you just recall. Here the three things are given. So you just recall the 4 equations. 4 equations of the LFRD format. Okay, great. That's all for final exam. Now you have some idea like which you need to figure it out and which you need to recall. So let's go to the format of the final exam. Now you have, I just no I just want to summarize all these things for you. From first 4 module, you will have most 2 and 3 marks questions. Most. Okay. So these 40 MCQs, that if you go through all the MCQ given to your assignments, you can easily solve 38, 39, or 40 questions. Great. And whatever we have discussed today. Now for the MSQ, 2 marks question up to fourth module, and mostly the simulation based technique, there the MSQ type of question will come. And the numerical type of questions, again the 10 questions, out of the 10 questions almost 3 questions will come from first 3 modules, 4 questions, 4 to 5 questions will come from this, and 3 questions again come from the form requisite algorithm, like what will be my beta, what will be my alpha, what will be the two, what will be alpha beta, and what will be my design point in X space. Clear? Now tell me, uh, what kind of issues you have. Now you have some idea, right? Just go through
Yes.
today's whatever I have given here. Just go through it, and the MCQ questions, all the assignments, go through them. But for the MCQs, and seriously, the final question, you just see the final question, you will laugh. Okay, the course is that tough, but the final exam is that easy. Okay, so don't need to worry about it. Okay, just go with that. But on a serious note, this is a very, very, very good and very effective course. If we want to do something out of the course, we need to go for some research base, or some project. We need to do some project as per reliability based, some design, or we can analyze some structure, we can propose something, or we can review all these things on some structure. Actually that will actually help us, that means you, Abdul, you are already working on reliability, Bob, you are already working on the structure. So like this problem, like if you have, we need to work on some live projects, or some projects where we can solve the things. Here we have learned the concepts, now we need to utilize the things, right? So how we can utilize these things, we need to figure out how we can fruitfully make or use the concept, and the things whatever we have learned during this course, because this course is advanced and rich with very cutting edge knowledges, how we can develop the reliability, or how we can ensure the reliability for the serious structures, or for the important structures, and all these things. Like this problem I want to actually demonstrate. But today, this kind of frame, like if you have any kind of structure, you can give it to me, or we can discuss over some meetings, like how we can use it, or how we can collaboratively develop some model out of this course, or how can like how can we, it's like not giving the exam and getting the certificate, right? For this course, yes or no? So
Yeah.
Yes. Very important.
until we have done uh, something tangible, then only we can say, okay, we have learned something from this course,
Yeah.
right? So that we need to figure it out. But for the final exam, just after seeing the question paper, you will laugh at you, like the course and this is like the question. And obviously out of this course, which kind of question we will say, if we will give the MATLAB kind of question, how we can solve, or how we can solve the numerical based or the simulation based technique here. So we need to work on some projects, do some or incorporate some knowledge, or incorporate some reliability approaches to that project, and figure it out. Okay, this will be my final model for the reliabilities, or we can propose some schemes of, like adaptive response surface, stochastic response surface. There are different kind of approaches, like here fourth moment approach they have come up with. Okay, here similar to your response surface method, but they have approximated with some moments. We can also figure it out, or we can simply use the existing model and work out with some live project, or some structure or something. Then that will make sense to ourselves actually.
Yeah.
So for that we need to sit, and after exam we can work out. And I also very much interested to do something with that course.
Same here. Even I'm interested to do that.
Yeah. So
I'm very, very interested. Actually, I had the same idea as
yeah,
you were
yeah.
talking
One
about.
more thing, like Bob, I'm calling him Bob, but he is very senior to me. Like he has for 23 plus experience in the structural engineering field. Okay,
Yeah.
so can all of you can on your videos so that we can see and we can like acknowledge ourselves. Then we will move to have like we are not like we all are like here Abdul, he is also PMRF fellow at IIT Hyderabad, and he's doing his research related to uh, slope stability, and there he need to add incorporate this knowledge uh, regarding that reliability. And Bob also, he's a structural engineer, and he almost 23 plus experience. That means he has seen all kind of situations. So you people said what we can do.
I think
Um,
we need to form a group, and
Yeah,
then after the exams, we have some team or meetings to come out with the approach, because I really think that it's a very important course, and actually it is not well practiced now. So
yeah,
it's a good area to expand. Particularly, India is even better. Africa, I don't think we are really doing more of this, particularly in my country. And I think that once we develop it, there will be a big consultancy approach
yeah.
to,
In India also
addressing some of the.
we stuck in the deterministic approach till now.
Exactly. The same here. Deterministic. Everybody deterministic. And once your deterministic approach is okay, nobody cares. But I think there is more to it than just going by the deterministic approach. So it's a good suggestion. And I think that we need to take it up. We can develop it and come out with something which I think will be beneficial to the engineering fraternity.
Yeah. And yeah, if we can develop something tangible, we can approach the Indian standard or the that codes, that okay, that kind of things you can incorporate. And here we have all the codes, all the concepts already ready. We just need to figure it out in which field we want to work them out, or we want to incorporate, and we can easily figure it out. And this field is totally untouched, not in Africa, in India also. The very few works have been done related to the reliability analysis, mostly for the nuclear buildings, that's all. But beyond that, we don't have that kind of reliability or facility analysis on incorporated to the structures or to the design purposes. And for the earthquake prone zone or the most vulnerable zones where the randomness is more, how we can optimize that randomness with respect to some optimization tool, or the reliability, how we can get the bigger reliabilities, we can figure it out. So it's like the codes we learn today, and you will give the exam. I think you have the exam on
it's on next Sunday, I believe.
next
Yet
Sunday.
to check it. I haven't received the phone numbers yet.
Yeah, but that's not the thing. Like we have all the codes and all these things ready. So it's like for me it's like that something is like not completed thing is there. So we need to figure it out, okay.
Yeah, we
And
can.
yeah, and we can easily figure it out, and we can do something. Yeah,
Maybe, as Mr. Bob suggested, we can create a group or something
yeah,
outside this uh, course, and then we can think about something and start working on it,
yeah,
distribute the work. And
yeah, exactly. For the foundation purpose, he Abdul is there also, me as a structural engineer, and he also is there. So yeah, we can figure it out something, and we can do something good.
sure. One more thing I want to, and I want to say this because I wanted to say it.
Yeah,
I'm really thankful to Mr. Devasis. Even though we are colleagues, even he is a PMRF, I'm a PMRF, but at the end of the day, you're a teacher as well, because I have benefited a lot from this course. So really thankful. Thank you. Thank
yeah,
you.
it's
Thank
it's my responsibility as a like as I'm the co-instructor of this, that TA of this course. So Like, yeah,
Thank you.
actually, it's very interesting course. That's why, I that attracts towards this course. Okay, develop the course, do it, and go deep into it. So that things are like sort of the fourth moment based approach. Also, I have developed this code for this fourth moment based approach, but I feel that okay, it's not that kind of things. So we need to
Mm.
work on that simulation based technique and the second order reliability. Even one more suggestion is there, how we can further incorporate to the nonlinear thing, that curvature thing. So we
Mm.
have lot of objectives to work on or to work with. So
I actually was working with this polynomial chaos expansion and Kriging's model. Recently, I was working on it. So what I've got is my predictions up to 3.5 beta value, reliability index up to 3.5.
mm,
The predictions are good, but when I pass 3.5,
yeah,
the predictions go just they are basically inaccurate
yeah,
up to
and
3.5.
one more thing I will add, like if you go below like 1 or 1.5, you will not have that convergence. You will have again the convergence issue.
Oh, okay.
So for some range, this
In my
reliability.
case, actually, in my case, I took 400 points and trained my models.
Okay,
So for values less than one, they're fine. But
okay,
anything above 3.5, totally inaccurate. I checked literature; they say something about subset simulations. I have no idea about it, but they suggest that if you go for subset simulation rather than simple MCS, it may help. But
yeah,
I don't know how to
yeah.
check that.
Yeah, and subset simulation, that's why I told you that subset simulation is a very good tool to work with the larger probability of failures where
Uh-huh.
we need to encounter with.
Okay.
So that's also because look, this work with the engineering structures, because most of the engineering structures the beta will fall between 2.5 to 3.5. Most
Yeah.
of the engineering structures. That's why that form based approach or the MCS based approach will give us the better results. But when we have the most nonlinear functions and the beta is larger or lower, then
Mhm.
we don't have. So for these cases, how we can ensure the reliability, that also can be the objective of
Uh-huh.
the further objective of the course.
Got your point.
Okay, good. I think that the first step is for us to share our WhatsApp numbers
Yeah.
Sure.
so that
Yeah, so you have my mail ID. I will share it to you, and Abdul already have my WhatsApp number.
Yeah, that would be fine.
Yeah.
uh I think why did you produce your WhatsApp number?
No. I personally share to him the WhatsApp number. I will mail my
I have
WhatsApp.
some questions. That's why.
Yeah, I personally, like I said to him, like you can directly call to me, rather mail to me. You can directly call to me and ask me the question. So that's why. And for Mr. Bob, I will mail my WhatsApp number to him.
Thank
Okay.
you.
Okay.
I think most of the mails I sent to you, I have my number in there.
Okay. You have
So you
that.
can share and
Yeah,
form
that
the
that
group.
that is my WhatsApp number. I have only one number. That is my call number and WhatsApp number. You can. Okay.
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 So I think I'm also very grateful. In fact, I've done about this is about the seventh or the eighth of the NPTEL course that I'm doing. And then I've never had such a cooperation as devices have produced. I'm really grateful and thankful because the support he's given is really, really, I mean, priceless. You can't put any value on it. And the desire to proceed after the course is also something you can't get from any of the courses that I have actually undertaken. So I think that it's a good thing. And then once we're able to proceed, I believe something good can come out of it. And then who knows? The next Nobel Prize winners will be the group, you
No, we
know?
are not thinking about
Eligible in
that.
the first
But
place.
we can do something tangible to this.
Yes,
Yeah, because this field is like still in the developing stage. Like what Abdul says, like in higher or lower liabilities, how we can work out, we can figure it out. Just we need to give some time, then we can easily find it out. Okay, this is happening, and if we know the cause, then we can find out the solution easily.
True.
That that's
definitely.
yeah. So Today we just conclude here. So I'm actually at my home for the puja vacation. I came. So after returning to the campus, you just go finish with your exam. Then we can talk and figure it out how we can proceed further. Okay.
Fine.
Okay. For
All right. Thank you very much.
Thank you.
thank you all for like attending. Like
Abdul,
you are attending
thank you.
continuously. That motivates me. Okay, let's do it further, dig it further. Okay,
Fine.
that's all. So thank you to you too also. Okay.
Okay.
Okay, then I'm ending the call. Thank you.
Fine.